Dear students, ਅੱਜ ਗੈਸ ਲਾਜ਼ ਐਂਡ ਕਿਨੈਟਿਕ ਥਿਊਰੀ ਦੀ ਇਸ ਕਲਾਸ ਵਿੱਚ ਤੁਹਾਡਾ ਸਾਰਿਆਂ ਦਾ ਸਵਾਗਤ ਹੈ। ਅਸੀਂ ਪਿਛਲੀ ਕਲਾਸ ਵਿੱਚ ਬਿਹੇਵੀਅਰ ਆਫ ਆਈਡੀਅਲ ਗੈਸ, ਲਾਜ਼ ਗਵਰਨਿੰਗ ਦਾ ਬਿਹੇਵੀਅਰ ਆਫ ਆਈਡੀਅਲ ਗੈਸਿਸ ਅਤੇ ਕਿਨੈਟਿਕ ਥਿਊਰੀ ਆਫ ਗੈਸਿਸ ਡਿਸਕਸ ਕੀਤੇ ਸਨ। ਅੱਜ ਦੀ ਕਲਾਸ ਵਿੱਚ ਅਸੀਂ ਕਿਨੈਟਿਕ ਥਿਊਰੀ ਆਫ ਗੈਸਿਸ ਦੇ ਮੁਤਾਬਕ ਬਿਹੇਵੀਅਰ ਆਫ ਗੈਸਿਸ ਬਾਰੇ ਪੜ੍ਹਾਂਗੇ। Before we start, let me share the learning objectives of today's topic.
On completion of this topic, learners will be able to discuss the gas law using kinetic theory of gas, state the expression for average value of energy for a gas in thermal equilibrium at a given temperature in 3 dimensions. Discuss the number of degrees of freedom possessed by different kinds of motion by the gas molecules. Explain the degrees of freedom and motion of monoatomic and diatomic gases. State the law of equipartition of energy. Calculate the molar specific heats at constant volume and pressure for monoatomic, rigid diatomic, non-rigid diatomic and polyatomic gases and the ratio of the 2 molar specific heat for each case.
According to kinetic theory of gases, the pressure exerted by the gas on the walls of the container P is equal to 1/3 of m by v into Vrms square, which is also equal to 1 by 3 nm Vrms square. However, half m Vrms square is the average kinetic energy of the gas molecules. If rho is the density of the gas, then P is equal to 1 by 3 into rho into square of Vrms, and the average kinetic energy of one molecule of the gas is 3 by 2 kT. With the help of kinetic theory of gases, it has been found that if temperature of the given mass of gas is kept constant, its volume is inversely proportional to its pressure, which is the Boyle's law. In other words,
keeping temperature constant, when we increase the pressure of the gas, the number of collisions per unit area increases and its volume decreases.
With the help of kinetic theory of gas, it has also been found that if pressure of the given mass of a gas is kept constant, then the ratio of V and T is a constant, say K, which is Charles' law. In other words,
keeping pressure constant, when we increase the temperature of the gas, its volume increases.
Again, with the help of kinetic theory of gases, it has been found that if volume of the given mass of a gas is kept constant, then the ratio of P and T is a constant, say K. This is Gay-Lussac's law. In other words,
keeping volume constant, when we increase the temperature of the gas, the speed of the molecules increase and the pressure of the gas also increases. And if we increase the pressure of the gas, its temperature increases.
आओ ਹੁਣ kinetic theory of gases ਦੇ ਅਨੁਸਾਰ perfect gas law ਸਮਝਦੇ ਹਾਂ. Since the pressure exerted by the 1 mole of gas is 1/3 of m by v into Vrms square, therefore PV would be equal to 1/3 of m into Vrms square. Here m by 3 is a constant, hence PV is directly proportional to the square of the root mean square of the speed of the gas molecules. According to kinetic theory of gases, Vrms square is directly proportional to absolute temperature. Hence, PV is directly proportional to the absolute temperature of the gas, or PV is equal to RT, where the constant of proportionality R is called the universal gas constant for 1 mole of the gas. Then, while trying to know the gas laws, Avogadro's law is as important as others to be learned. To do so, let us consider two gases A and B having equal volumes V at the same values of pressure, say P, and temperature, say T. Let m1 be the mass of each molecule, Vrms1 be the mean square velocity, and n1 the number of molecules of the gas A in volume V. Similarly, m2 be the mass of each molecule, Vrms2 be the mean square velocity, and n2 the number of molecules of the gas B in volume V. Then, according to the kinetic theory of gases, m1 n1 into square of Vrms1 is equal to m2 n2 into square of Vrms2. क्योंकि दोनों गैसेस सेम टैंपरेचर ते ਹਨ, इसलिए गैसेस ਦੀ kinetic theory अनुसार गैस A ਲਈ एवरेज kinetic एनर्जी पर मॉलिक्यूल गैस B ਦੀ एवरेज kinetic एनर्जी पर मॉलिक्यूल ਦੇ बराबर होनी चाहिए है, ਜਿਹੜੀ कि 3/2 के T ਦੇ बराबर है. In other words, m1 into square of Vrms1 should be equal to m2 into square of Vrms2. This shows that n1 is equal to n2. Thus, equal volumes of all the gases under identical conditions of temperature and pressure contain same number of molecules, which is the Avogadro's law. According to the kinetic theory of gases, the rate of diffusion of a gas is directly proportional to root mean square velocity of its molecules. Let R1 and R2 are the rates of diffusion of gases A and B respectively. Then the ratio of R1 and R2 would be equal to the ratio of Vrms1 and Vrms2, or the ratio of the square root of rho 2 and rho 1, that is, the rate of diffusion is inversely proportional to the square root of the density of the gas, which is the Gram's law of diffusion. In other words,
keeping same temperature, same pressure, same volume and same average kinetic energy, molecules of lower mass have higher velocity, whereas molecules of higher mass have lower velocity. In other words, rate of diffusion is inversely proportional to the square root of the density of the gas.
ਕਿਸੇ ਸਿਸਟਮ ਦੇ ਕਨਫੀਗਰੇਸ਼ਨ ਨੂੰ ਪੂਰੀ ਤਰ੍ਹਾਂ ਡਿਸਕ੍ਰਾਈਬ ਕਰਨ ਲਈ ਕਿਨੈਟਿਕ ਥਿਊਰੀ ਆਫ ਗੈਸ ਨੂੰ ਹੋਰ ਮੋਡੀਫਾਈ ਕੀਤਾ ਗਿਆ. ਇਸੇ ਤਰ੍ਹਾਂ ਡਿਗਰੀ ਆਫ ਫਰੀडम ਦਾ ਕਨਸੈਪਟ ਇੰਟਰੋਡਿਊਸ ਹੋਇਆ. The degrees of freedom of a system are defined as the total number of coordinates or independent quantities required to describe the position and the configuration of the system completely. For example, a point mass has a one-dimensional motion. The point mass moves along a straight line only, say along x-axis. Its position can be specified by its displacement along the x-axis. Therefore, such a point mass has one translational degree of freedom. If the point mass has two-dimensional motion and say that it is moving in the xy plane, then its position at any instant can be determined by knowing the displacement of the point mass along the x-axis and y-axis. Thus, it has two translational degrees of freedom. When the point mass has three-dimensional motion or it is moving in space, its position at any instant can be determined by knowing the displacements of the point mass along x-axis, y-axis and z-axis. Now, such a point mass has three translational degrees of freedom.
For example, the bob of an oscillating simple pendulum has 1 degree of freedom. An insect moving on a horizontal floor has 2 degrees of freedom, and a buzzing bee has 3 degrees of freedom.
ਜੇ ਬੋਡੀ ਰਿਜਿਡ ਅਤੇ ਫਾਈਨਾਈਟ ਸਾਈਜ਼ ਦੀ ਹੋਵੇ ਤਾਂ ਟਰਾਂਸਲੇਟਰੀ ਮੋਸ਼ਨ ਦੇ ਨਾਲ ਹੀ ਇਸ ਵਿੱਚ ਆਪਣੇ ਐਕਸਿਸ ਦੁਆਲੇ ਰੋਟੇਸ਼ਨਲ ਮੋਸ਼ਨ ਵੀ ਹੋ ਸਕਦਾ ਹੈ। ਟਰਾਂਸਲੇਟਰੀ ਮੋਸ਼ਨ ਦੀ ਹੀ ਤਰ੍ਹਾਂ ਰੋਟੇਟਰੀ ਮੋਸ਼ਨ ਵੀ ਸਪੇਸ ਵਿੱਚ 3 ਇੰਡੀਪੈਂਡੈਂਟ ਕੋਆਰਡੀਨੇਟਸ ਨਾਲ ਡਿਸਕ੍ਰਾਈਬ ਕੀਤਾ ਜਾ ਸਕਦਾ ਹੈ। ਸੋ ਇੱਕ ਰਿਜਿਡ ਬੋਡੀ ਦੀਆਂ 6 ਡਿਗਰੀਜ਼ ਆਫ ਫਰੀडम ਹੋਣਗੀਆਂ, 3 ਤਾਂ ਟਰਾਂਸਲੇਟਰੀ ਮੋਸ਼ਨ ਕਾਰਨ ਅਤੇ 3 ਰੋਟੇਟਰੀ ਮੋਸ਼ਨ ਕਾਰਨ। ਇਸ ਆਬਜ਼ਰਵੇਸ਼ਨ ਦਾ ਜਨਰਲਾਈਜੇਸ਼ਨ ਕਰਕੇ ਇਹ ਕਿਹਾ ਜਾ ਸਕਦਾ ਹੈ ਕਿ ਇੱਕ ਡਾਇਨਾਮਿਕਲ ਸਿਸਟਮ ਦੀਆਂ ਡਿਗਰੀਜ਼ ਆਫ ਫਰੀडम ਮੇਜਰ ਕਰਨ ਲਈ ਕੰਸਟੀਚੂਐਂਟ ਪਾਰਟੀਕਲਸ ਨੂੰ ਸਪੈਸੀਫਾਈ ਕਰਨ ਵਾਲੇ ਟੋਟਲ ਨੰਬਰ ਆਫ ਕੋਆਰਡੀਨੇਟਸ ਵਿੱਚੋਂ ਨੰਬਰ ਆਫ ਇੰਡੀਪੈਂਡੈਂਟ ਰਿਲੇਸ਼ਨਸ ਨੂੰ ਸਬਟ੍ਰੈਕਟ ਕਰਨਾ ਹੋਵੇਗਾ। In a system of n particles, if the particles possess k independent relations between them, then the number of degrees of freedom of the system F is given by 3n minus k. Let us calculate the degrees of freedom in some cases. First of all, we take the example of monoatomic gas molecule. Helium, neon, argon, etc. are the monoatomic molecules as they consist only one atom. A monoatomic molecule can be considered as a point mass as it is capable of translatory motion only. In such a case, n is equal to 1 and obviously k would be 0. Hence, degree of freedom for monoatomic gas is 3. Therefore, a monoatomic gas molecule has 3 degrees of freedom. Let us consider the case of a diatomic gas molecule. Hydrogen, oxygen, nitrogen, etc. are diatomic molecules and have 2 atoms in each of them. The molecule is capable of translatory motion of its center of mass. So, it has 3 degrees of freedom due to translatory motion. Apart from these, the molecule can rotate about 2 perpendicular axes also. The rotatory motion therefore contributes to more degrees of freedom. In a diatomic gas molecule, the 2 atoms are held at a fixed distance by the molecular bond. Here, n is equal to 2 and k is equal to 1. Hence, a diatomic gas molecule has 5 degrees of freedom. Similarly, we can find out the degrees of freedom for a triatomic gas molecule. Sulfur dioxide and hydrogen sulfide are triatomic molecules and have 3 atoms in each molecule. In a triatomic gas molecule, the 3 atoms are held at fixed distances relative to one another by the 3 molecular bonds. In a linear triatomic gas molecule, 2 atoms lie on either side of the central atom. Thus, n is equal to 3 and k is 2. Therefore, a linear triatomic gas molecule has 7 degrees of freedom. But in a non-linear triatomic gas molecule, the 3 atoms are held at 3 vertices of a triangle. Therefore, n is equal to 3 and k is also equal to 3. Hence, a non-linear triatomic gas molecule has 6 degrees of freedom. ਅਸੀਂ ਜਾਣਦੇ ਹਾਂ ਕਿ ਕਿਸੇ ਵੈਸਲ ਵਿੱਚ ਗੈਸ ਐਟਮਸ ਜਾਂ ਮੋਲੀਕਿਊਲਸ ਦੀ ਕਲੈਕਸ਼ਨ ਨੂੰ ਥਰਮੋਡਾਇਨਾਮਿਕਲ ਸਿਸਟਮ ਕਿਹਾ ਜਾਂਦਾ ਹੈ। ਰੈਂਡਮ ਮੋਸ਼ਨ ਵਿੱਚ ਗੈਸ ਐਟਮਸ ਜਾਂ ਮੋਲੀਕਿਊਲਸ ਦੀ ਕਿਨੈਟਿਕ એનર્ਜੀ ਉਹਨਾਂ ਦੀ ਡਿਫਰੈਂਟ ਟਾਈਪਸ ਆਫ ਮੋਸ਼ਨ ਕਾਰਨ ਹੁੰਦੀ ਹੈ। ਸੋ ਗੈਸ ਮੋਲੀਕਿਊਲਸ ਦੀ ਕਿਨੈਟਿਕ એનર્ਜੀ ਉਹਨਾਂ ਦੇ ਟਰਾਂਸਲੇਟਰੀ ਮੋਸ਼ਨ ਜਾਂ ਰੋਟੇਟਰੀ ਮੋਸ਼ਨ ਜਾਂ ਵਾਈਬ੍ਰੇਸ਼ਨਲ ਮੋਸ਼ਨ ਕਰਕੇ ਹੋ ਸਕਦੀ ਹੈ। Kinetic energy of translational motion. A gas molecule possesses kinetic energy of translational motion due to its linear motion. It is given as Et equal to half mv square, where m is the mass and v is the linear velocity of the gas molecule. Kinetic energy of rotational motion. The kinetic energy possessed by a gas molecule due to its rotational motion about an axis is called its rotational kinetic energy, and it is given as ER equal to half I omega square, where I is the moment of inertia and omega is the angular velocity of the gas molecule. In case the gas molecule is treated as a point mass, for example a monoatomic gas molecule, then I is equal to 0, and hence such a gas molecule cannot possess kinetic energy of rotational motion. However, for a diatomic gas molecule, moment of inertia may not be 0, and therefore such a gas molecule can possess kinetic energy of rotational motion. Kinetic energy of vibrational motion. किसी गैस मॉलिक्यूल विच वाइब्रेशनल मोशन करके पैदा हुई kinetic एनर्जी इस दी वाइब्रेशनल kinetic एनर्जी अखवांदी है। वाइब्रेशनल मोशन सिर्फ वेरी हाई टैंपरेचर ते ही पॉसीबल हुंदा है। घट टैंपरेचर ते गैस मॉलिक्यूल दी kinetic एनर्जी ज़्यादातर ट्रांसलेशनल जां रोटेशनल मोशन करके हुंदी है। डू यू नो that the degrees of freedom of a gas molecule can also be determined by knowing the number of ways in which the gas molecule can absorb energy. In other words, the degrees of freedom of a system can also be defined as the number of independent modes of absorption of energy by the particles of the system. Let us calculate again the degrees of freedom of a monoatomic and a diatomic gas molecule. Let us start with monoatomic gas molecule. A monoatomic gas molecule can absorb kinetic energy of translational motion along each of the three axes and hence possesses 3 degrees of freedom corresponding to translational motion. Whereas the monoatomic gas molecule, being a point mass, cannot absorb kinetic energy of rotational motion and hence does not possess any degree of freedom corresponding to the rotational motion. Therefore, degrees of freedom of a monoatomic gas molecule are 3, which is same as calculated earlier. Let us now take the case of diatomic gas molecule. Let a diatomic gas molecule be lying along y-axis. It has a non-zero value of moment of inertia about the axis OX and OZ, but moment of inertia of the molecule about the OY axis will be 0. Hence, it will possess 2 degrees of freedom corresponding to its rotational motion and to each mode of absorption of rotational energy about OX and OZ axis. Besides this, there are 3 more degrees of freedom due to its translational motion corresponding to each mode of absorption of translational energy along all 3 axes. Therefore, the total degrees of freedom of a diatomic gas molecule are 5, which is the same as calculated earlier. However, at a very high temperature nearly equal to 5000 Kelvin, the vibrational motion excites up in the gas molecules. In such cases, the diatomic gas molecule possesses 2 more degrees of freedom corresponding to its vibrational motion, and the degrees of freedom of a diatomic gas molecule would be 7. However, Boltzmann also described the law of equipartition of energy. According to the law of equipartition of energy, for a dynamical system in thermal equilibrium, the energy of the system is equally distributed amongst various degrees of freedom, and the energy associated with each degree of freedom per molecule is half kT, where K is the Boltzmann's constant. To prove it, let us consider 1 mole of monoatomic gas in thermal equilibrium at temperature T, and let the mass of the gas molecule is m. We know that each gas molecule has 3 degrees of freedom due to its translational motion. According to kinetic theory of gases, the mean kinetic energy of translational motion of a gas molecule is equal to 3/2 kT, that is half m Vrms square equal to 3 by 2 kT. Let Vx square bar, Vy square bar and Vz square bar be the components of mean square velocity of the gas molecules along the three axes, then average energy of a gas molecule would be half m Vrms square equal to half m Vx square bar plus half m Vy square bar plus half m Vz square bar, which is equal to 3 by 2 kT. The molecular motion is random in nature and no direction of motion is a preferred one. Therefore, the average kinetic energy corresponding to each degree of freedom is the same. It means half m Vx square bar is equal to half m Vy square bar, which is also equal to half m Vz square bar. On solving, we get half m Vx square bar or half m Vy square bar or half m Vz square bar is equal to half kT. Therefore, the mean kinetic energy per molecule per degree of freedom is half kT. We can measure the specific heats for monoatomic or diatomic or triatomic gases also. First of all, let us calculate the specific heat of a gas. Let us consider 1 mole of a gas. Let each gas molecule possess f degrees of freedom. As 1 mole of the gas contains Na molecules, therefore, the total degrees of freedom of the system would be NaF. If T is the temperature of the system, then according to law of equipartition of energy, amount of kinetic energy per molecule per degree of freedom is equal to half kT. Therefore, total kinetic energy of the system E would be equal to NaF into half kT. Since Na K is equal to R, the gas constant for 1 mole of the gas, hence total kinetic energy of the system E would be equal to F by 2 into RT. Let Cv be the specific heat of 1 gram mole of the gas at constant volume and dE be the small amount of heat energy required to raise the temperature of 1 gram mole of the gas at constant volume through a temperature dT. Then dE is equal to Cv into 1 into dt, or Cv is equal to dE by dt. On substituting the value of E, we get Cv equal to d by dt of F by 2 RT. On differentiating, we get Cv is equal to F by 2 into R. This is the general expression for the molar specific heat of a gas at constant volume. Let Cp be the specific heat of 1 gram mole of the gas at constant pressure, and we know that for an ideal gas, Cp is equal to Cv plus R. On substituting the value of Cv, we get Cp equal to F by 2 into R plus R, that is 1 plus F by 2 whole into R. This is the general expression for the molar specific heat of gas at constant pressure. We can also measure the ratio of the two specific heats of the gas. We know that the ratio of two specific heats of the gas Cp and Cv is equal to gamma. On substituting the values of Cp and Cv, we get gamma is equal to 1 plus 2 by F. Knowing the value of R and the degrees of freedom of the gas, we can calculate the molar specific heat at constant volume and at constant pressure along with the ratio of two specific heats. Now we calculate the values of Cp and Cv and gamma for monoatomic, diatomic and triatomic gases. For this, we substitute the value of F in the expression of Cv, which is equal to F by 2 into R, Cp which is equal to 1 plus F by 2 into R, and gamma which is equal to 1 plus 2 by F. For a monoatomic gas, F is equal to 3, hence Cv is equal to 3 by 2 into R. Cp is equal to 5 by 2 into R and gamma is 5 by 3. On substituting the value of R, we get Cv is equal to 2.98 calorie per mole per Kelvin, whereas Cp is equal to 4.96 calorie per mole per Kelvin. For a diatomic gas, F is equal to 5, hence Cv is equal to 5 by 2 into R, Cp is equal to 7 by 2 into R and gamma is 7 by 5. On substituting the value of R, we get Cv is equal to 4.96 calorie per mole per Kelvin, whereas Cp is equal to 6.95 calorie per mole per Kelvin. Similarly, we can find these values for a triatomic gas. For a triatomic gas, F is equal to 7, hence Cv is equal to 7 by 2 into R, Cp is equal to 9 by 2 into R and gamma is 9 by 7. On substituting the value of R, we get Cv is equal to 6.95 calorie per mole per Kelvin, whereas Cp is equal to 9.83 calories per mole per Kelvin. However, these calculations are for a linear molecule, but for a non-linear molecule, F is equal to 6, hence Cv is equal to 3R, Cp is equal to 4R and gamma is 4 by 3. So, we are near the end of today's topic, but before that, let us summarize its content quickly. According to the kinetic theory of gases, pressure exerted by the 1 mole of the gas is 1/3 of m by v into v RMS square. Therefore, PV would be equal to 1/3 of m into v RMS square. Hence, PV is directly proportional to the square of the root mean square of the speed of the gas molecules or directly proportional to the absolute temperature of the gas, or PV is equal to RT, where the constant of proportionality R is called the universal gas constant for 1 mole of the gas. This is the perfect gas equation. If temperature of the given mass of a gas is kept constant, then its volume is inversely proportional to its pressure, which is the Boyle's law. If pressure of the given mass of a gas is kept constant, then its volume is directly proportional to its absolute temperature, which is the Charles law. And if volume of the given mass of a gas is kept constant, then its pressure is directly proportional to its absolute temperature, which is the Gay-Lussac's law. Graham's law of diffusion states that the rate of diffusion of two gases are inversely proportional to the square roots of their densities. If ρ1 and ρ2 be the densities of two gases and Vrms1 and Vrms2 be their respective root mean square velocities, then ratio of the root mean square velocity of gas A and root mean square velocity of gas B is equal to the ratio of the square roots of density of gas B and density of gas A. Since the rate of diffusion of a gas is directly proportional to root mean square velocity of its molecules, therefore, the rate of diffusion is inversely proportional to the square root of the density of the gas. Degrees of freedom of a system are defined as the total number of coordinates or independent quantities required to describe the position and configuration of the system completely. In a system consisting of n particles, if the particles possess k independent relations between them, then the number of degrees of freedom of the system F is given by 3n minus k. According to the law of equipartition of energy, for a dynamical system in thermal equilibrium, the energy of the system is equally distributed amongst the various degrees of freedom, and the energy associated with each degree of freedom per molecule is half kT, where K is Boltzmann's constant. General expression for the molar specific heat of a gas at constant volume is Cv equal to F by 2 into R. General expression for the molar specific heat of gas at constant pressure is Cp equal to 1 plus F by 2 into R, and the ratio of the two specific heats of the gas Cp and Cv is equal to 1 plus 2 by F. Let us have a quick test to find out how much you have actually absorbed. Question first, define mean free path. Answer is average distance covered between two successive collisions is called the mean free path of the molecule. Next question is, give the expression for specific heat at constant volume for a monoatomic gas. Answer is Cv is equal to 3 by 2 into R. Next question is, give the expression for specific heat at constant pressure for a diatomic gas. And answer of this, Cp is equal to 7 by 2 into R. Next question, give the expression for specific heat at constant pressure for a triatomic gas. And answer is, for a linear molecule, Cp is equal to 9 by 2 into R, and for a non-linear molecule, Cp is equal to 4R. I am confident that you have understood the topic well and enjoyed the lesson. Thank you for your attention and see you next time.